Okay, so welcome everyone to today's PhD seminar. Our speaker today will be Alberto Caron. His supervisors are Ioanna Manolopoulou and Gianluca Baio. And today he'll be talking about Bayesian learning in the counterfactual world. So thank you, Alberto.
Over to me, I guess. Thanks a lot, Alessia, and thanks for inviting me here. Yeah, this talk is going to be like very high level, so we're all on the same page, and hopefully it's not going to be boring as it seems. So this has been basically the work I've been doing for my now like 3 years of PhD with my supervisor Ioanna. Ioanna is my first and Gianluca is my second. And yeah, so the very tentative schedule of the talk is this one. I'm just going to focus more like the first 3 chapters, and then if there's some time left, I can go through the 4th one, which is like going to be like a conference paper. It's a bit like less material, but let's see how it goes on with time. Okay, so as you can see from actually, if you could see like from my title, the talk would be on Bayesian Non-Parametrics and Causal Inference, and how to use actually the first one to actually carry out the second. The very broad sort of like 2 lines definition of causal inference is understanding how like intervening on a random variable affects another random variable y. So we're going to call z basically our like manipulative or like action variable, and y is going to be like our outcome variable. Sort of like there's 2 different main different type of studies that we can get from actually carry out causal inference. The first one is randomized experiment, which is sort of like the gold standard for causal inference. It's the gold standard because you actually go out in the real world. So think about like a medical treatment. What you do is just basically go out in the real world and give the treatment out randomly to your sample. So there's going to be like completely artificial allocation of the completely random, allocation of the treatment. So there's not going to be any self-selection or selection biases whatsoever. So you have a nice, nicely, well-behaved sample where you can actually carry it out this sort of like causal effect estimation. The problem with randomized studies is that they're really costly, and in general, exploration of policies in the real world is really costly or simply unfeasible sometimes. On the other side, we have observational type of studies, which are abundant in many disciplines, but they're flawed by selection bias, of course, because like people, for example, self-select them into treatment, or there's some like a weird and unknown selection mechanism into treatment. Okay, like think about like any other type of medical study where people just select them into treatment. Where the ML side comes in is just basically when we have very high dimensional data. So that's going to help like shrink down or regularize very complex function when you have like very high dimensional data. Okay, but we're going to see more of this later on. So our aim, the aim of the work we've been doing is just basically come up with some estimation of causal effect at a very fine resolution, which means like a patient level type of treatment effect. This is interesting in like many disciplines because you have, most time, I mean, treatment is not homogeneous among patients. So like condition on patient characteristics, you have like very different type of causal effect, okay, of treatment effect. So putting this into notational and into notation and context, suppose we have like a continuous outcome, a binary action variable, or treatment variable, let's call it this way, and then we have some high-dimensional vector of covariates which include confounders. So confounders as basically are common causes of z and y that sort of like mess up your like causal effect of interest, which is the effect from z to y. Okay. Also, on top of that, we're going to use the Rubin causal models, which allows us to define these 2 quantities here, which are potential outcomes. So potential outcomes are two like different, in this case, two like different version of the outcome in different state of the word. So for example, y1 is going to be like the state of the world where individual I got the treatment. Y0 is the other state of the world, so the counterfactual state of the world where the individual didn't get the treatment. Okay, so the main problem of causal inference is that only one of those two outcomes is actually observed, and the other one is never observable in the real world. Okay, as I said before, we're interested in like very fine resolution type of treatment effects. So we have we can define this quantity, which is conditional average treatment effect, which is basically the difference between the average difference in the two potential outcomes, conditional on patient characteristics. So very high dimensional. You can think this, electronic health records, for example, where you have like a lot of patient characteristics, which are like age, comorbidities, and other stuff. As opposed to the typical estimator, which is a population average treatment effect, which is going to be marginalized over the covariates, so not taking into account the patient characteristics. Okay. This slide is actually showing you a very simple one-dimensional one confounder example. So essentially, we have one covariate which is affecting the selection into treatment. So in the first graph, you have, for example, for higher values of X, you have like people being selected with higher probability into the treated group, and for lower value, you have people only in the control group. So you have basically undersampling in those regions for one of the treated group. This is obviously of interest because there's like in this region, you're lacking a bit of a comparison unit. So units with the same type of characteristics, but being selected in either of the treated group. Also, like we have like some response, like different responses, Y for the treated group and the control group, essentially. So just mentioning that the gray dots are actually the counterfactual outcomes. So they're for each kind of like covariate value, we can observe like only one of those counterfactual outcome, and the other one is never observed. So the never observed one is actually the gray dot. So from these quantities, we can actually define the individual treatment effect as a difference between the two potential outcome, which is all gray because it's never observed. So we cannot fit like a supervised learning model, for example, directly on that. While Kate in this case is the black dashed line function, essentially. So it's like average, okay? So you got like some noise around that, and you want to find out what's the underlying mean or like that function. Okay, so this slide is sort of like I know there's some people like in the department doing some like reinforcement learning, and this is sort of like trying to link. There's I think like a different literature, focusing on this problem. One literature is like some like sub branches of reinforcement learning. So and this is also like to introduce graphs which are really helpful, so you kind of like understand what's going on in different cases. So if we take like a randomized experiment, we have like no influence of X on Z because Z is actually artificially set, and like people are randomly selected into treatment or not. That's the case. That's the like static IID case. So if we introduce the dynamic, so that the time dimension on that, this is going to be seen as like a multi-arm bandit. The same thing for observational study. So the one we focus on, if you sort of like move away from the static IID case and you introduce a time dimension, that's going to be called, I think, contextual bandits. So you sort of have like a sequence of observation, which are not really, which can be actually IID, or if it's over time, you can have like same, for example, you can have like same patient, and you can have like some dynamic treatment rule where that you want to, like learn or estimate. And then we have like the whole case of like a standalone case of reinforcement learning, where you have like some sort of like loop-in interaction between the context and the action space, and then you observe some reward, which is which can be easily sparse. So think of a game of chess, for example, where you move around the chess board, and you're gonna have like a reward only at the end of the game, essentially. Okay, so this is just to link a bit of like causal inference with reinforcement learning. And the case we're going to focus on is the B case, so the static IID case with observational studies, so where you have like some confounders, common causes of Z and Y. Okay, cool. And obviously, in that case, to sort of identify the causal effect from Z to Y with the quantity that we're given, we need some assumptions. I'm not going to go through into this one's like in details, but the two main assumptions are actually unconfoundedness and overlap. So unconfoundedness is just basically saying that, assuming that we observe all the possible confounders. So this is a bit of a stretch in some designs. Obviously, it's less of a stretch if you think like of like I-dimensional, when you have like I-dimensional covariate space. So like electronic health records, because the sort of like underlying assumption to that is that you observe enough proxy variables to kind of like counterbalance or like take into account all the possible unobserved confounders. That's the main like underlying assumption. The other main assumption is overlap. I sort of like introduced this earlier, but using this definition of a propensity score. So propensity score is the probability of being selected into treatment given your patient characteristics. Okay, so it's like sort of like describe the selection mechanism. Overlap means that quantity, that probability is strictly between 0 and 1. What it means is that you like no deterministic selection into treatment. So you have like a theoretical guarantee that your counterfactual outcome actually exists. Okay, so you have like a sort of like no deterministic selection. So you could have observed that individual in the other treatment group. So this is the most general assumption of overlap assumption. There are some other like stricter type of assumption in overlap. So under this two main assumptions, so unconfoundedness and overlap, we can actually write the potential outcome, any potential outcome statement into like transfer into like a conditional event statement. So we can write actually Y1 as the Y being conditioned on being selected into treatment. So that's the main step when we do the when we take into account all the assumptions. And so essentially K can be defined as two, like the difference between two expectation conditional on the treatment status and the I-dimensional patient characteristics. Okay, so now it's the point to kind of like introduce ML in this. So this sort of like there are like many ways where you can come up with a K estimator, like using ML methods. These sort of like routines of like algorithms, they're called usually meta-learners. So they're sort of like meta algorithms using some other base learner algorithms, such as random forest neural networks or other like Bayesian or regularized type of black box non-parametric models. And they sort of like fit a function of obviously X and Z in general to kind of like fit the outcome eventually. So the most so S&T learners are very preliminary work on the fill. You can see that we can actually classify all the meta-learners two main classes, which are direct and propensity method. So the main difference is that propensity method actually, like sort of like produce an estimate of propensity score, and they use it somehow in estimation to, counterbalance or take into account the effects. This is sort of like we've done reviewing all the kind of like state-of-the-art meta learners work in the field. Obviously, like it's a very kind of like dynamic topic. So you get literally tons of different like meta learners. I'm not saying every week, but like every month, like somebody come up with a different procedure doing that, which has like some pros and cons, etc. So I'm just gonna like quickly run through this list, without like actually like going into details about like each method. So these are the two very preliminary words. So S learners and T learners, and S learners is just vanilla type of method. So if it's a single surface, which is a function of X and Z, and it sort of like switches on and off the button of treatment, and that takes the difference. So just basically you have a single function, and then you take the difference by switching on and off the binary treatment variable. The T-learner conversely is doing some like the opposite thing. So it takes the whole sample, it splits it into two different groups, and then treat it as independent and fit like two completely different function, F1 and F0 in this case, and then takes the difference. Like for example, in this case, we're using BART to do this, to the one confounder example that we saw before. Obviously, like here, T-learner, you can actually use you can use like different learners on each treatment group. Like for example, the control group here would have benefited more from obviously like a simple linear regression, for example. So you can actually use a linear regression here. You can use some other like more complex or like non-linear method for the treated group. Then we got X learner, which is 2017, I think. It's sort of like an extension of T-learner, which uses some propensity score estimates to counterbalance the difference in sample size between the treatment groups. So this works well when you have like very unbalanced design, and which can actually happen a lot of times in observational studies. So usually you have like, for example, the treatment group, which is a very very few observation, and then you have the control group, which is larger. So using propensity score actually helps you out with the sort of like fighting overfitting and underfitting in either of the two groups. R learner is kind of like a semi-parametric type of method because it uses a different parameterization of the Kate function, of the outcome function, and it's sort of like break it down into two main quantity, which are mu, which is the prognostic score, and Kate itself. So it's sort of like you add a parametric, semi-parametric assumption basically, but you end up with a outcome surface which features directly the Kate function in it. And this is actually, the Bayesian are sort of like seen as in a Bayesian way, but this is not Bayesian, so they do plug in. So they estimate all the quantity, come up with some sort of like a revisited version of the outcome surface, where you sort of have a loss function directly on Kate. So if you're using any type of like parameter tuning on your method, you have a nice framework where you have you can sort of like tune parameters directly on the Kate function. The multitask learners. It's a class which uses multitask learning. I mean, self-explanatory, but to sort of like view the two potential outcome surfaces coming from the same functional space. So in this way, you can sort of like you still have two different models, so F1 and F0, but you have some sort of like correlation. You're allowing correlation flowing into these two type of function. Usually it's done with GPs, which sort of like serve themselves well to multitask learning in this case. And the last one is tau learners. Tau learners is actually using the same outcome parameterization as the R learners, but it's using in a Bayesian way. So it's sort of like use the same parameterization and see this as a sort of like a linear regression where mu is the intercept and tau is the slope. So you can actually place a Bayesian prior on the tau function directly. So and this is nice for some reasons we're going to see later. Okay, as I said, like I'm not going to be going into like details about pros and cons, but if we want, we can go more later. So our contribution to the big two methods. So one of the method is BCF, so it's Bayesian Causal Forest, and it's a version of tau learners. And the other is an extension of Causal GP. This is going to be like the last chapter, so I don't know if I'll have time to actually go through that. But let's focus on the BCF side first. So BCF, Bayesian Causal Forest, employs obviously trees and forest, by the name, and employs particularly a very popular type of like Bayesian ensemble method, which is called Bayesian additive regression trees. To sort of like start from the beginning, a tree, we all know it's like a collection of binary split rules that essentially splits down partition the covariate space into smaller regions, very like homogeneous, and takes the average inside these regions to sort of like build up an estimator for the outcome y. So this is like a simple decision tree. On top of that, this type of like ensemble method, such as like gradient boosting, for example, in the supervised learning literature, what they do is just basically putting together this weak learners. So they use, for example, very shallow and small decision trees, and then they sort of like put them together to develop a very strong learner of the outcome surface. And the type of like weak learner part is has to do with avoiding overfitting. So you sort of like very simple learner that by themselves they're not really explanatory of the relationship between x and y, but when you put them together, it's going to end up having like stronger nice properties. Bayesian additive regression trees is the same thing as gradient boosting, but seen in a Bayesian way. So you have the final estimate of your function is a sum of m different trees, and each of these trees is basically explaining a small portion of variability in the x-y relationship. In this case, G, for example, G is a tree function which maps the covariate space x to the final nodes in the tree, where T is actually the tree structure, so the collection of binary split rules, and M is just basically the collection of final nodes inside the tree T in that case. So I'm just going to give a bit of an overview of how inference is done in BART very quickly. So inference is obviously Bayesian. The sort of the parameters are the tree structure, obviously, and the final like leaf parameters in the tree structure, m times, because you have like m different trees, and then you have the variance of the error term. So the inference is done through an MCMC, very simple MCMC, which is made of a block deep sampler and a Metropolis Hastings. So the Metropolis Hastings is used to actually build up the tree structure, and how this is done is just basically it proposes a new tree structure using like a branching process. So you sort of have like with some discrete probability, you have some action which you can take on a tree, like you can swap binary split rules. You can sort of like grow another rule at the end of the tree. You can actually prune the tree and these sort of things. And you sort of like take a likelihood ratio there to construct a Metropolis Hastings with some acceptance ratio, and you sort of like move through these like tree structure space. well enough. After that metropolis HTM step, you just sort of like block sample all the final nodes in the tree. So, and this is just like Gaussian conjugate type of step. And then you have like an inverse gamma, of course, like conjugate step for the variance. Okay. The particular thing which is of interest to us is that the kind of like the binary splitting rules in a tree, so the covariate upon which the tree splits are chosen randomly in the normal BART, so the default BART. So you just pick one covariate randomly and you build like a binary split rule out of that. So this is not very like in the early days of BART, this was not really well seen because it could like it led to very poor mixing in the sort of like branching process, because like you're really visiting a part of the you're mixing poorly, so you're visiting like very few possibilities when it comes to like splitting rules in the trees. So the as I said before, so BCF is built upon BART, and the way this is actually employing BART is by putting like two separate BART priors on the outcome surface, specifically on the prognostic score mu and the tau function. So in this way, you like exploiting this outcome reparametrization, you have like separate independent BART prior, and this is very useful because to sort of like avoid something which is called regularized induced confounding and unnecessarily large variance on your Kate estimator. And I'm going to make the case why. So if we take the t-learner, for example, where is that? So if we take a t-learner, so we feed like two separate BARTs on the F1 and F0, our Kate estimator will be like the point, the point-wise estimator, like the point-wise difference between these two functions, okay? So the variance on the Kate estimator will be the sum of the variances, like totally like different variances of these two estimators, minus, like 2 times the covariance, of course. But, in this way, if we don't model the variance of Kate, we end up with a very unnecessarily large variance. So, for example, in the one covariate case, for example, in this case, you see that like there's no, variance around ITE. It's just basically, can be relatable to the variance of the single surfaces. So it's not going to be the sum of variances of these two surfaces. So that's why, like fitting a T type of learner with some Bayesian shrinkage is going to lead you to have some sort of like an unnecessary large variance. And obviously, like we don't care only about like point-wise estimation as Bayesians, but not only as Bayesian probably. So this is the main actually gain of utilizing BART with a BCF structure. On top of that, the second thing which is the main characteristic of BCF is that BCF is a propensity method and employs a propensity score estimate as a plugin in the following way. So it estimates propensity score with some probabilistic classifier, whatever, and then it plugs it into the prognostic score function as an additional covariate. The sort of like the main idea, so the general idea of why is that you sort of like propensity score is a well-behaved, let's put it this way, one-dimensional reduction of the covariate space. So if you're like, if you're not observing all the confounder, you can sort of like try to plug in a propensity score to take into account of all the other unobserved confounders, hoping that your propensity models is good enough to actually account for the variability also of the unobserved confounders. And this is also like on a lower level, this is also done to mitigate with targeted selection. And targeted selection is a type of selection bias where basically you have that people are selected into treatment based on otherwise adverse outcome. So imagine like a doctor prescribing a medicine to a patient just because he fears it would have been worse otherwise. And of course, like provided that this medicine doesn't have a lot of side effects, of course. This is sort of like a type of selection bias. And you can clearly see how this leads to have a direct relationship between propensity score and prognostic effect, where prognostic effect is actually the effect, forgot to say this, is the effect of X and Y in absence of the treatment. So if you place this to 0, you end up that actually the explanation is, everything is explained just by prognostic effect, okay? So in this targeted selection case, we have that, propensity score is a direct function of a prognostic effect. So the expectation of otherwise adverse outcome without the treatment. Okay, so this is the general framework of BCF, right? And with our extended method, which is called shrinkage Bayesian causal forest, so shrinkage BCF, we sort of like wanted to answer the type of question, what are actually the main drivers, the main moderating effect behind treatment heterogeneity, right? First of all, and second of all, also to kind of like speed up computation in BCF as another side effect. The way this is achieved is through some Dirichlet, some hierarchical beta Dirichlet priors, which gonna triggers another like Dirichlet step in the MCMC, obviously, as a conjugate. And this Dirichlet prior is placed on the splitting probabilities in the predictor. So basically, the idea is that while in BART and BCF, splitting rules are chosen randomly, so splitting covariates are chosen randomly, and this leads to poor mixing. In DART, so Dirichlet additive regression trees, we're gonna split more. So the aim is to split more on the most predicted covariates. So we sort of like gain a lot of computational time by avoiding splitting on very unnecessary or very irrelevant predictor. On top of that, we're gonna end up also with with some additional output, which are posterior splitting probabilities. Posterior splitting probability are actually stick breaking probabilities, and they can be viewed sort of like as a measure of feature importance in the end. So while this is not a really a sparse type of method, it's gonna adjust very well to sparse underlying sparsity, so sparse TGPs. This is just a couple of examples, which shows obviously that our method is nice, of course. So this is just not only like in high-dimensional situation, of course. For example, this method is just comparing bias and PE, which is basically root mean square error on treatment effect. The other example I think is more interesting, this one, because it's sort of like explain the main difference between having a like S learner, T learner, BART or DART prior, and having like a shrinkage BCF prior. So in this example, we have just 5 predictors, of course, and 3 of them are totally irrelevant for the estimation. The first 2 are relevant, but are relevant in 2 different ways. So the first one is relevant for prognostic effect, and the second one, X2, is actually a moderator of treatment effect, right? So the thing is that if we use a S or T learner here, we're sort of like selecting the correct variables. We're not selecting them, we're not allocating them to the right bucket, okay? So while BCF by construction sort of like split down or break down the outcome into prognostic and treatment effect, so you sort of like end up with something which is selecting the correct relevant predictors, but also like putting that in the right bucket. Okay, so this is a x1 is a prognostic. It's a prognostic variable, while x2 is a moderating variable. Okay, so this is the main idea. Yeah, the next couple of slides is just a real-world application of shrinkage BCF. So we have this infant health development program data where you have some binary treatment, which is pediatric visits, and Y, which is the IQ test score of the child. We have like a couple of observations, and we have 31 pretreatment covariates, which are going to include, of course, like some confounders. Sort of like what we end up with is a graph. So I'm going to focus on the second one first. So these are the posterior probabilities from shrinkage BCF and on treatment effect on the Kate function. So it's basically answering the question: what is the most predictive? What are the main drivers of heterogeneity behind this treatment effect in patient characteristics, for example? And this turned out to be, like, for example, this 29th and 31st. So moderate ethnicity and moderate education level in this case. You can see also, like, you can see obviously that these are like steep breaking probabilities. So they're not, so it's not actually doing variable selection per se. So you cannot actually place them, set them to 0 directly. So you just have some probabilities which are higher than others. So it's not really a sparse method, but it's going to adjust to pretty well to sparse DGPs. On the first graph, instead, like this is just a graph highlighting the heterogeneity in treatment effects, or the heterogeneity patterns. We have so we're subgrouping by propensity percentile. So we just estimate propensity score as a function of the characteristics, and then we group, we group the observation by propensity percentile and see what's the subgroup effect. So averaged inside that percentile by group. So this is pretty much, explaining how heterogeneous is the treatment effect across the sample, essentially, with a one-dimensional reduction of the covariates, which is propensity score. Okay, so I don't know, I'm doing on time because I lost track for a second, but this is sort of like supposed to be the last part. Yeah, I think like I'm just going to take like 2 minutes just to introduce that, and then we can skip to questions, obviously. So as I said before, our second work is extending the class of multitask type of like meta-learners, and particularly the class of this class of like multitask Gaussian processes. As I said before, the interesting view on the problem of Kate estimation from a multitask perspective is that you have like your fitting to function f1 and f0, which come from an underlying same functional space. So you sort of like treat this as a vector valued function. So you treat Kate as a vector valued function, of course, so all the two potential outcome function, and you're going to place a Gaussian process prior, which has some multitask kernel K that has like some typical Gaussian processes parameters. On top of that, you have also the kind of like correlation parameters. So the idea is that you learn these parameters, you can adjust to different degrees of similarity that you have between the two potential outcome functions. Okay, this is a pretty nice example. So this is like a similar, very similar one-dimensional, one covariate example that we saw before, but this case is we have like the potential outcome function are both exponential, so they're like quite non-linear function, but the Kate, so the difference between these two functions is actually constant. Okay, so they just translated by a constant, but because of like undersampling, or put in other words, non-overlap in some regions, so the extreme region, you end up sort of like, if you do like just like GP estimation, like independent estimation, you end up like messing it up, for example, here, because you're not going to follow the true underlying function in the undersampling space, undersampling region. While if you force multitask learning, you can borrow information from learning into this treated group and sort of like raising this lineup to follow up on this like constant treatment effect. Obviously, like your underlying assumption here is that the treatment effect has simple patterns, and in this case, it's like very simple, so it's like constant. But in it's believed in most applied studies, believe that like treatment function Kate is going to display simpler patterns that, for example, the prognostic function, which is going to be even more complex, at least relatively. So the main problem with using GP is obviously because they scale poorly with high dimensions, so both with sample and predictor space. Also, since we're doing multitasking over the action here, that's not going to scale well with increasing action spaces as well. So for a different problem, for a different reason now, because we have over-parameterization in that case. And the sort of way to tackle this, or we thought about tackling this, is through these models which are called deep kernel models. The main idea of these models is that instead of like applying a GP directly on the input space, you just learn a lower dimensional representation of the input space. And then you have like 100 predictor, you learn a lower dimension, which is like maybe say like 2, 3 dimensional hidden space, and you place a GP there. So in this case, you get rid of anything, all the instability problems with matrix inversion by having like a very low dimensional space. So this is nice also because it can accommodate also designs when you have multiple correlated outcomes. So things about like medical design where you have some like side effects, for example, probability of like having an heart attack and also bleeding, which are two negatively correlated outcomes. And you can also sort of like force multitasking over the outcome as well. Like, so you have like 2 layers of multitasking, which is over the action and then over the outcomes as well. Yeah, this is some example, but I think I can skip that, honestly. And yeah, that was pretty much it. Hope I didn't bore you to death. I mean, I tried my best.